Good morning, everybody. We're going to do something a little bit different today, and we are going to put the main part of our presentation into this video here so that our class time today can be mostly focused on working through problems and being able to ask questions during that process. So the video itself, I'm just going to go over briefly what are the main topics that we went over this year. And if you guys would just kind of work through these things and listen to it, I'm going to show you a bunch of resources. And then that way in class and on our asynchronous day, we can maximize our time doing actual practice problems and getting ready for our tests that we're going to have for the final exam. So yeah, just jumping into our lesson today, we are going to be using the 2 days, Monday and Tuesday, and both of these are just going to be doing the same task basically, which is completing the Honors Physics final exam review, which you guys will submit into Google Classroom. And so I'm just like generically saying just do half on both days. One of those days will be in class, one will be at home. As far as what's due, this actual package will be due at the end of the week. And so you'll want to have this all worked out in your journal and turned in. As we're working through and reviewing for our final exam, I want to point out that pages 1 through 60 in the online textbook, the PDF of the textbook, there's a bunch of good resources in there. I'd recommend that you open up that textbook while you're doing your work and just flip through those pages and notice what topics relate to the questions at hand. And when you're struggling with them, it gives you something to look at. We also would want to have our IB physics equations handy, ready to go. On the test, you will be able to use these equations. Now, the first section that we worked on this year was dealing with like basic math from physics and measurements and vectors, some of those mathy topics. So there's some notes here. There's these conversion notes and measurement notes. These are things that you can lean into during those types of questions to say, okay, here's some resources to look at, and that'll help you out. So some of the main things we looked at with vectors is can you use right triangle trigonometry? And so I just give you an example right here where you have got what are the x and y components of this vector. And so if you notice right now, the vector is in a 90-degree triangle, and it's 6 newtons going off at 30 degrees, and it's sort of like north of an east-facing line. And if you wanted to go ahead and figure out those opposite sides and those adjacent sides, the opposite side uses the sine of the angle equals opposite over hypotenuse. In this case, the hypotenuse is 6, so it'd be like 6 sine of 30, give you this blue vertical arrow, and then 6 cosine of 30 would give you the red arrow. Okay. Now, another way that we can look at resultant vectors from our sides is if you have just like a triangle like this one here, you just use Pythagorean theorem, where you've got a squared plus b squared equals c squared, and you could figure the c squared out, which is the hypotenuse, which is also the resultant vector. You could just do it as the square root of 4 squared plus 3 squared, which is a 3, 4, 5 triangle. So that would actually be 5 newtons would be your hypotenuse. So another thing that we do is we add vectors together. And so if you notice, you've got 2 different vectors right here. And if you put those 2 vectors together, you could go ahead and come up with a resultant. And it's kind of shown right here. And so what you would do in this case, you could just go ahead and take your x and your y components, just like we showed in that first one, and get the x components and add them together, or possibly subtract them. Okay, in this case, there would be subtraction because they're going in the x toward each other. And then you would add the resultants that are going in the y together to come up with that black arrow. So you notice like the x components would have actually canceled in this case, and the y components would have added up to that black arrow. So those skills are embedded through much of what we do through physics. So you want to make sure that you're okay on those. You'll see a few questions on our final exam that deals with vectors as part of other problems. The next big topic we got into was kinematics. So kinematics uses our main kinematics equations here, and understanding what these equations are and how to use them is going to be really important. I've given you a bunch of resources. Now, when I notice these resources, I say they're optional, but these are things that are going to help you get on top of topics that maybe you're rusty with. So I've included like topic notes here. I've included a concept video. I've also included a problem-solving video here. Again, nothing required here, but these are things that could definitely help you out to get ready for a test. I also went ahead and included all of the different notes that we did throughout the whole entire kinematics unit. So we've got velocity notes, graphing, motion, acceleration, horizontal, and angled projectile motion. So again, there's notes in here. You could open those up in a separate tab. And when you're working on a specific problem and you don't know how to deal with it, you could just go right into those notes and see how they deal with it. Now, some people are better with videos, so I went ahead and included two videos here, 1D kinematics and 2D kinematics, that really just goes through, each one is about 16 minutes long, and it just steps through the whole process of how do you solve kinematics problems, and it gives you all the topics and stuff that you might see on our test. When we were looking through kinematics, we had a problem-solving template here that just shows you the main steps of how do you solve kinematics problems. Anything from like starting with a picture or a free body diagram, identifying all of your known variables, and then the known variables they don't tell you, like gravity or zero start speeds, things like that. And then also going ahead and identifying the formula that works for the variables you have and the unknown, solving algebraically just for the letters, just for the symbols of the formula, and then finally putting in numbers. So that problem-solving format can help you get through problems that you might not initially know how to figure out just by looking at the question. All right, now getting into our kinematics unit, we had some big ideas. One of them was with distance and displacement, this idea of the vector versus the scalar nature of position change. And so notice in the bottom here, I've got some notes to help remind you of what those things are. But noticing that displacements are vector, distances are scalar. And then we have an idea about speed versus velocity. Okay, so remember how speed was distance over time, so it's a scalar and it doesn't care about direction, and velocity was a vector and it did care about direction. Okay, and then that led us into this idea of acceleration. And so there's some notes again down in the bottom here in the shared notes to think about acceleration. The basic version of acceleration is change of velocity with respect to time. And like going in this circle right here, you can change velocity just by changing direction too. So getting on top of the concepts of acceleration is important. We did a lot of work with graphical analysis. And so like if I look at a graph, one of the first things I do is I ask, well, what type of graph am I looking at? In this case, I'm looking at displacement with respect to time. And I notice that the slope is what we would call velocity or speed. And the linear slope, the fact that it's straight right here, means we have a constant velocity or a constant speed going on. And that idea of the slope, it was connected to the calculus idea called the derivative, but really it's just the slope. That's all we need to know about it, and you should be able to take the slope of a distance versus time graph. The next step is a velocity versus time graph. When you take the slope of that, we're talking about acceleration. That's the definition of acceleration, is change of velocity over time. So your slope is acceleration. And then we also get into this idea of area under the curve, and sometimes we call that integrals. And the area of a velocity time graph is displacement. Okay, so remember how we did that work before, going up in our derivatives, down in our integrals. Taking area, velocity of time, will give you the change of position or the displacement. Now, a straight line is constant velocity, constant acceleration. That's what I meant to say. Okay, next one we see here is acceleration with respect to time. And mostly what we deal with in our class is just going to be constant acceleration. So you notice these constant accelerations, but the area here is going to be your change of velocity. So that's the area for an acceleration with respect to time graph. So just remembering those characteristics. Now, when we are doing problem solving, it's important that we can go into our formulas and identify formulas that are going to work with the variables we have in our problems. And so notice right here we've got velocity, initial velocity, acceleration, time, S is distance or displacement, A is, we said that, acceleration. Yeah, we got all this now. So just kind of remembering what all the formulas are. How do we use these things? Make sure you're familiar enough to jump right into questions using your kinematics equations. We talked in this unit about projectile motion. We looked at some of the conceptual ideas of projectile motion. Remember, some of the keys to projectile motion was that you break your problems up into horizontal and vertical parts. And for the horizontal components, there's no net forces acting on these problems. The horizontal components just have like a constant horizontal velocity that acts throughout the problem. And when we solve problems with those horizontal velocity, it's just using the formula for velocity equals change of position over time. Okay, and so then the vertical components right here, which when we break it up into a triangle, that's going to be our v sine of theta vertically. And that component right there is acting in a gravitational field, and it's actually being accelerated or decelerated in that case by gravity. And so we have to put those two things together for a projectile problem. I'll show you an example on the next page. But a couple things to notice conceptually. When we have a projectile, it'll form this symmetrical parabola, and the two sides will be the same as long as we have no friction acting in the question. Additionally, when you get to the top of your flight up here, you have eliminated all of your vertical velocity. This would be the sine component, and you're just left over with your horizontal velocity, which is like v cosine of theta at the top. And the time that it takes to go up is the same time that it takes to get down when you land at the same height. Okay, so just a few things to remember conceptually. Sometimes in our questions, you may have a question that asks you what would be the effect of friction on a parabola or on your projectile motion. Now, we don't do any math problems with friction and projectile motion. That gets very complicated. But when we look at these differences of like position changes, vertical velocity, horizontal velocity, you can see how friction will actually have an effect on a projectile. Now, one of the main types of mathematical problems that I'm going to give you on this test coming up is going to be dealing with a horizontally launched projectile. In the class, we did this as that tabletop lab where we were trying to hit our target on the ground. And with this one, you always want to break your problem into parts. And one of the first things you do is look at just the y parts and solve for time, and then look at your x parts and use the horizontal velocity formula to solve for a range or a distance. And I went ahead and just worked out this problem here with an example. If you had a change of y of 0.75 and a speed of 1.5, so notice how those would go into here. What would be your range? And then I just worked through a problem completely to give you an example of how that works. Okay, next unit we went into was the dynamics unit, and that was where we were using Newton's second law as one of our main formulas, and the formula for force of friction is equal to mu normal. Now, this unit right here had some conceptual questions related to Newton's first law of inertia, second law, which is the F equals ma, and third law that says for every action there's an equal and opposite reaction. And then beyond those, we also went into some practice problems solving with free body diagrams and calculating accelerations of a system. And so I've got some resources. So again, these resources here are not something that's required, but it's something that can help you. We've got some notes about the topic too in general, and a detailed forces notes. I've got a video here about Newton's laws and forces, and there's also a worked out problem set. It's just like it has a key and it shows you like how to work out specific examples. And again, that's just for extra support as you work through your review. I also went ahead and included this video here from Khan Academy about the whole unit. And again, that's just like a 17-minute video right there. Not required, but it could definitely help you out. Additionally, I've got all the notes that we used during the unit right here for you. So when you get into the Newton's laws type examples, you want to start by drawing free body diagrams. And so there's some conventions with free body diagrams that we followed. Always draw your picture as like a generic little picture. Start with a dot at the center of mass. All of your vector arrows have their tails originating on the dot, and then they go out in their requisite directions. Any real forces are going to be solid arrows. Components of real forces will be dotted arrows, and you want to go ahead and use your drawings, break everything up into X and Y, go ahead and put positives and negatives on there to make sense of the directions, and then assess your sum of forces for equilibrium. Excuse me. The next thing we do here is kind of follow this problem solving strategy right here, and really like going through identifying your formulas. If you do have a state where you are in equilibrium, you're going to set a sum of force equation where all of your forces add up to 0. And if you find out that you're in non-equilibrium in either X or Y, then you're going to set all of your forces equal to mass times acceleration according to Newton's second law. Now you make an assessment with equilibrium in both the X and the Y perspective, and oftentimes you're going to have to break apart components of angled vectors into their XY components by using sine and cosines of angles. And be really careful about your positives and negatives. Okay, that's your basic problem solving technique. Now, one of the essential things that we did during this unit was we assessed how free body diagrams work on inclined planes. And I had you guys memorize that the horizontal, in the sense of like coming this way here on the slope here, and the vertical components right here were based on weight. We would break weight up into those components, and then everything else would fit in an XY plane. And I gave you just the example here of how that works. And so notice in your X plane here, you've got mg sine of theta and friction acting. In the y, you've got mg cosine of theta and normal acting. So just remember that is an important aspect of how do we solve a lot of these types of problems. So I gave you a couple of examples here just to remind us of the problem solving. So here's an example of a person falling into a net. Now, as they hit the net, they were going pretty fast, and you can imagine that the net would slow them down. And so the fact that they're slowing down says that there is an acceleration, and the acceleration is actually directed upwards. Okay, and so if you're going to do a free body diagram of that situation, you'd notice that the up arrow is bigger than the down arrow. You'd start off by writing a sum of forces equation for the y perspective, and it equals ma. And then you notice that your normal force, which is directed up, and your mg, which is directed down, add up to ma, solve for normal force, and then you got your answer. Okay. I gave a couple more examples here, one on an inclined plane and one with two dogs fighting over a bones. And notice how I went ahead and just drew the free body diagrams, do the sum of forces equation, come up with a final answer. And then the last one is using the coefficient of friction. This question was asking you to recognize it between static and coefficient of friction. When the box is accelerating, you would be accelerating with your force being resisted by kinetic friction. Okay, that's because it's actually sliding at this point. And I go ahead and show you the work right here, but because acceleration is equal to force over mass, and I did an assessment with a free body diagram of force of push compared to force of friction. Remember, friction is mu normal, so I'm defining this as mu mg on the flat, and I got my forces add up to an acceleration here, and you can see it. And so that's basically it. That's just the review for today. And the actual test itself will be next week on Monday and Tuesday. And it'll be probably, I'm just sort of still defining it right now, but maybe something into the realm of 30 questions that just go over the whole range of what we've done in this unit. And the review for the finals right here. And so with this review, you're going to want to set it up in your journal. You're going to create a title. Then you're going to go ahead and number the problems as you work through them. I want you to show your whole entire solving process. Some questions that are just straight up conceptual questions, explain your logic, and then write your answer down. Now, once you've written down your answer, you're going to go ahead and check your work with the key at the back, see if you're right or not, and then make corrections to get to the right answer. Okay. Now we'll have some definite in-class working time, so I'll be going around the class working with you. You can also go ahead and give me a message in Google Classroom. So just to show you what the paper looks like. So this is our assignment here. This is what you're going to upload into Google Classroom. And you can see it kind of shows you like the percentages of where the questions come from on the test. It gives you all the different topics that we've studied this year. And then it starts in on the questions. And notice the questions here. There's like question 1, multiple choice. In your journal, you just show the work, put your answer down, and do like a whole chunk of them, like maybe like 5 in a row. And then at the end of that little work session, you're going to go ahead and check out the back here, the very end. And I've got all the answers right there. So you're just kind of using this as like a back and forth to check your work. Now, throughout the whole entire week, this is going to be due on Sunday. So I'm assigning this on Monday. So that's like a whole week, basically. You got 84 questions to work on. So kind of break up the work over the week. But especially on our work sessions on Monday and Tuesday, we should have the majority of it done. But you can still continue through the week as review. So that's it. So this is the end of our first quarter. I can't believe it went so fast, but here we are. So you guys have a really good day. Enjoy yourself.